Başladığını da bir görelim. Evet. Okay. Welcome all. Today I will be introducing the A-star search algorithm. A-star search algorithm is a shortest distance. It's an algorithm to solve shortest distance path problem, as Dijkstra's algorithms does. A-star is pronounced as A-star, and it can be used as an alternative to Dijkstra's algorithm. The difference between Dijkstra's and A-star algorithm is Dijkstra calculates the shortest distance of every node to the source node, but A-star is only concerned about the distance between source and target. So, of course, Dijkstra will. You may think that Dijkstra is capable of, calculating every possible distances from the source, and in the meantime, A-star is only concerning one the target source. Target node. This may look like a bit disadvantage, but actually, if we are trying to plan a route between source and target and the shortest distance, A-star will be focusing on one task, and it will be a lot quicker than Dijkstra's algorithm. Once again, it is used to find the shortest path between two nodes of a weighted graph. So A-star algorithm is working on the graphs, and those graphs should have weights on the edges. And the last thing, A-star's search algorithm performs, it is a lot quicker than Dijkstra's algorithm because its use of heuristics, it says. A heuristic is probably a new word for you. It is, in Turkish, it is called sezgi. How can I describe it? You have got some intuition about what you can do while solving the problem. So probably you will have, if you have got some prior knowledge about the subject, for example, when you go out, imagine that you want to go to cinema, for example, and you want to, you are starting from your house. You just get out of your house and you have to turn either right or left or go straight forward, for example. There are three options. And even though you have never been in cinema before, maybe you know that the cinema is on the left-hand side. So rather than trying right-hand side, going straight forward, you may start searching from the right-hand side because you have got a prior knowledge, maybe sometimes, for example, you are searching for a food or searching for a shelter and you get lost, and you are on the on a mountain or a hill, whatever it is, and you want to find a shelter where you can sleep and maybe have a food. And while searching, while looking, you see some smoke coming out from a certain place, and you may have an intuition that could be a chimney, a house. It can be because of a chimney, and there may be a house in that direction, rather than going any random direction. Because you have seen that smoke, you direct yourself to where the smoke is coming out. So that is heuristic, that is intuition, that is sezgi in Turkish, because you have got some prior knowledge that if there is a smoke, there may be a house. Of course, it can be something else. It may be resulting of some other causes. But since we have got some, even though it is not a definite information, that little information may help us to find a shelter if we need one. Anyway, A-star algorithm is once again a greedy algorithm, and while evaluating which node to visit next, it uses a fitness function. It uses a function fn, and that evaluation function is equal to gn. Fn is equal to gn plus hn. Gn is the path cost function, which is the cost from the starting node to the current node. We will be talking about this later. And Gn is the actual cost coming from the source to the current node. Let me write it down for you. Imagine that we have got nodes like this. Okay. And this is a weighted graph. There is a connection between these two, maybe this two. Imagine that this is a node as well, just a coincidence. And let's say it is something like this. Okay. The connections are like this. Imagine that we have got a weighted graph, and we have got some weights, let's say 4, let's say 10, etc. And this is our source. We start from here, and let's say this is our target. Okay, so that is the node n. The n in here means the current node. Okay, the current node Gn is the total distance, total shortest distance between the source and the current node. So if the distance between this node and that one is 4, and that is 10, let's say this is 5, the shortest distance between S and N is 4 plus 4, which is 8. So the value of Gn is 8. Hn is the heuristic distance. It is not the actual distance, but your estimation about the current node's distance, estimated distance to the target node. So if you are, for example, if you want to go to Ankara from Adana, okay, and you are in Aksaray, and you know, because you already passed through Aksaray, from Adana to Aksaray, you already traveled, and you know the actual cost of going to Aksaray. Therefore, Gn is a known, a crisp value. It's a certain value, certain distance, certain cost. And when you are in Aksaray, you are asking someone that how far is Ankara to Aksaray? So Ankara is to Aksaray, yes. And the person says that I think it is 250 kilometers, for example. He is not giving you a certain value, but giving an estimation. Therefore, if we have got that estimation, if we have got that prior knowledge, I should say, or an extra knowledge, by integrating into decision mechanism, using as an HN, heuristic value, we estimate, let's say that person says that the target is how much, let's say 7 unit is far away from the target. So the actual cost of going, starting from S and passing through N and reaching to T target is actually 4 plus 4, that is 8, plus the heuristic value of 15. So we can say that if we start from S and pass through N by following the shortest distance, then going to target will cost us almost 15 units. Okay, the cost is 15. That 15 is that value is not a certain value. It is still an estimation because there is an heuristic part in it. And therefore, we are not talking about the actual cost of reaching from source to target. We are just making an assumption, a rough estimation of going from S to T by using node N. Node N is the current N, current node. So what it is, A star doesn't guarantee you the best solution, but it usually finds the best solution. It is because it has got an unknown situation, some estimation that may lead you to somewhere else, some other direction, and it may cause, you may not find the optimal solution, but near optimal solution. Therefore, what we should know, Dijkstra definitely calculates the shortest distance between two nodes, okay, from source to any target node. But A star doesn't guarantee you the best score, best path, but mostly it works out. And what is the trade-off for this? The trade-off is because we are spending so little time to calculate the path, we can, how can I say, using A star will be more beneficial to solve complex problems within a short time, even though it is not optimal solution. In here, I will not be reading all of them because there are lots of explanation about why we should use priority queue or how we will implement, etc. But what we should know, this is the important part. While making the estimation, if you remember, we were in N and making an estimation to T, that estimation, the actual cost, it is not the actual cost, that estimation has to be lower than the actual cost. What I mean is, your estimation should be what was the exact word? Underestimate. You should estimate the total distance between the current one and the target. It should be underestimated. For example, if you remember from the Aksaray analogy, I was asking to going Aksaray. If the person says that the distance is 250 kilometers, and that person knows it, because we are using as an heuristic, you should accept this information as 240, lower than the actual value. Never overestimate the distance. If you know that the distance is 250, you should never estimate 260. That is the disastrous one. Therefore, whenever you make an estimation, your heuristic value should be underestimated. That's the most important thing while solving the problem with A star algorithm. Anything else? Okay, it is greedy algorithm, and there is an animation in here. From a starting point to the target point, Dijkstra's algorithm is trying to solve problem every single possible case, and A star algorithm is going by using the direction because it knows the actual, it has gotten heuristic information. At the beginning, as you can see, it is directly moves towards the source, but later then when it comes to an obstacle, it tries to pass over it. As you can see, once it finds the way, it reaches to the end. Let me show you let me demonstrate you an application to compare A star algorithm with Dijkstra's algorithm. Okay, this is, I mean, they are exactly the same mazes. Okay, let's call that maze. And imagine that we have got a robot. We have got a robot which is trying to find its path through these obstacles to reach a certain place. Okay, and that robot has got some sensors that is capable of knowing how much is the distance, you know, crow fly, kuş uçumu in Turkish, crow fly distance to the certain to the target. If the robot knows the crow fly distance to the of the current node to the target node, it will be, you know, by having this heuristic value, it will be a lot faster than finding the path than Dijkstra. Let me play it for you. Now, that is the destination, that red dot, okay? And the robot will start from that green node. As you can see, A star algorithm is, how can I say, shooting up towards towards the destination. Dijkstra is trying to solve every single possible cases from the radiating from the starting point. I'm not interfering anymore. Let me demonstrate. Now A star has found, and Dijkstra is calculating, and in the end, it is finding the path. Check it. Okay, another one, maybe. Now the problem is more complex because it changed the size of the cells, so there are so many cells. It will be, you know, more complex for the robot to find to navigate to the endpoint. Let me show you. That's the destination. Found it. As you can see, it is, I told you that maybe the path it found, it may not be the shortest, but because it is so fast that the trade-off is, in a short time, it calculates a near optimal solution. So it's creating some obstacles for the, anyway, you can check this video later on if you like, by writing compare A star versus Dijkstra. You can, let me show you. That is the search terms, A star versus Dijkstra, and you will come across with this video, and you can watch it by your own time. Anyway, let's go back. So after promoting that A star is a lot faster than Dijkstra, let's see how the algorithm works. Okay, the question is, by using A star algorithm, find the shortest distance between the current node, starting node A to target node Z. So we want to find out what is the shortest distance between A and Z. Also, we need to find out the path, as in the case of Dijkstra's algorithm. So what we need in order to solve with A star search algorithm, we need some intuition, we need some heuristic information. So these values are given by the nodes are the prior knowledge or our estimation of the distance from C to Z is 11. For example, let's see E and Z. We are in E and the estimated distance to Z is 4. This is our heuristic value. Someone has to supply you with those numbers, or if you are the one who is giving the decisions, then you have to supply those heuristic values rather than another person. Okay, I'm saying that this information should be given to you because you may be hired to solve some problems for an engineering problems for a company, and they are the one who knows what are the relations between the cases and what will be the costs between them. And of course, they should make an estimation of reaching to the target node. You may not have that information, therefore you should be supplied with it. And even though there are 7 nodes in here, so it may be easy for you to make an assumption, but if the problem search space is very large, that could be a problem for you to prepare. So you need some information from the person who is hiring you. Anyway, the important thing, E and Z, the actual distance is 5 and our estimation is 4. As I told you, we have to underestimate it. You shouldn't be estimating it as 6. For another thing, between the distance between D and Z is the actual distance is 7, and as you can see, it has been estimated as 6. You may estimate this as 5 or 4 because as long as it is smaller than the actual cost, that's fine. But your estimations should be as possible as possible correct as the actual one. Therefore, your estimation that your heuristic value is greatly affecting the performance of A star algorithm. Okay, let's calculate. Let's start. If in the past I asked such questions in the exams, if there are so small amount of, I mean, less nodes in our graph, you can arrange your solution as a table, okay? But if it is large, extremely large, in the case of this, as in the case of there are so many cities, in this case, preparing a table will be, time consuming. Then you can directly work on the graph. That you can work on the graph and list, or you can list your solution as if using some phrases, etc. I will show you later on. Now, let's start. That is our current node. We are starting from A and we want to reach node Z. And since this is an algorithm very much like Dijkstra, what we are doing currently, we listed all the nodes from A to Z. After that, the shortest distance from A. So if you remember, let me write it here. Fn is equal to Gn plus Hn. Gn is the actual cost of reaching N from the starting point plus heuristic distance or heuristic cost from the current node to the target node. Now, shortest distance from A to A is 0. Okay, heuristic distance is 14 and it has been given. and total distance will be 0 plus, Fn will be 0 plus 14. The total distance will be registered as 14 to the table. And there is no previous note because we have started from A. The next step is we should, as in the case of Dijkstra, A is connected to B and C. So we should calculate the shortest one. So the distance to B, let's check. It was infinite at the beginning, and what we have found, 4. 4 is smaller than infinite, so it is shorter. Therefore, reaching to B will not be infinite anymore. We will be updating it as 4, and that will be updated as 3. So they have been updated as 4, reaching to B as updated as 4 and 3, as in the case of Dijkstra, okay? And how about the total distances? Since reaching B is actual cost is 4 and the estimated cost is 12 to the Z, deprem oluyor diye arkadaşlar durdum, kusura bakmayın. 4 plus 12 will be 16. So the total distance will be 16. And how about this one? 3 plus 11, it will be 14. And we are taking a note that, as in the case of Dijkstra, we were saying that we reached B with that value by using, by coming from A. So we noted that previous note was A. Now, since the algorithm is greedy, what we will be doing, the cost, we will check the costs. They are 14 and 16. I'm checking the Fn values. Please be careful. We are checking Fn values. So C is the shortest one. By the way, we are finished with A. So we will say that it is visited and we will not be dealing with anymore. So we will be expanding C and checking the cost of reaching Z through ACEZ or ACD, by using those nodes. So the node A has been visited, so we ruled it out. And we are at C, and reaching E, let me check, reaching E was infinite, as in the case of Dijkstra. So reaching E will be from A to E through the C will be 3 plus 10, the actual cost. Therefore, it will be 13. 13 is larger than infinite, so we will put 13 here. And how about D? 3 plus 7 is 10, and reaching D is infinite. 10 is better than D, so 10 is better than infinite, so we will update it as 10 and 13. Therefore, we updated them as 10 and 14. How about the cost of reaching from source to target by using these nodes? It will be, let me talk about the cost of E. The actual cost is, by the way, we have to take the note that we are coming from C in order to obtain these values, okay? Because the value we calculate is reaching E through the C. Therefore, I put those marks. Anyway, so reaching the actual cost will be 10 plus 3, that is the GN value, 13, plus the heuristic value 4. Therefore, reaching, the estimated cost will be, the Fn will be 17 for E. And how about this one? 7 plus 3 is 10, and adding the heuristic value, reaching to Z will be, by using D, from A to Z, by using D will be by using this and reaching here will be 17, right? Sorry, 16, and we have put 16 there. So we are finished with C. We were finished with A. Now we are finished with C as well. So we put that to visited queue, visited list. So we will never deal with it anymore. After that, the number of active nodes are, let me show you, by the way. It was like this. We were in A. The active nodes were B and C. We checked B and C. What have we have done? We are finished with this. Then the available nodes were D and E and B. And when we calculated the total distances, we check whichever is the smallest. Then we put that one, put the node C visited list. Therefore, we are not dealing with it. And among the B, E, and D, whichever is the smallest, because it's a grid algorithm, we will go over there and carry on, activate the nodes if there is any. So we were here, we calculated B and E. Now let's check. Not the visited ones, because we are done with them. Sorry, yes. And not visited nodes are, the costs are, FN values are 16, 16, and 17. Which one is the smallest? 16. Either of them can be selected. What we will do, we will select B randomly. And after reaching B, we will be expanding B and E. E has been visited before, and the value was 13 through the C, because we were coming from E through the C, and the cost was 3 plus 10, 13. Now there is another path from B, 4 plus 12, 16. 16 is not smaller than 13. Therefore, we will not update it. We will not be using that one. Therefore, we will not reach E through the B, but C. Therefore, previous node will remain as C, because reaching from B will be expensive than reaching through the C. Similarly, we will check the value for F, fitness value. And what is the actual cost? The actual cost is 4 plus 5, that is the G value, which is 9, plus the estimated value 11. 11 plus 9 will give us 20. And by the way, 4 plus 1 will be 9, and 9 will be smaller than infinite. Therefore, we will update it, and we will update that the previous node. It is, we are reaching F through the B. Therefore, we have to write B here. Now, we use B, C, and A. Among the open list, which they are F, E, and D. Let's check. The cost of F is 20. The cost of E is 17, and the cost of D is 16. Therefore, which one will be selected? D will be selected. Okay, because it is not visited yet. The next step is go to D and expand it. Currently, we are at the D, and we can only reach to E because these are already visited, so that's why they are blacked out. And from D to E, we have to calculate, as in the case of Dijkstra. The actual cost is 3 plus 7, which is 10, and reaching to E will be 12, and 12 is better than the actual value, which was 13, so we will update this value, and we came to E through the D, therefore we will update D as well. Now, how about the cost? The actual cost is 3, 7 plus 2, because that is the shortest distance. That is 12 plus the estimated value. 12 plus 4 will be 16. So the estimated value will be 16. And we updated it. And from now on, we will not be dealing with D as well. So it will be blacked out. And the remaining open ones will be E and F, F and E. So because the algorithm is greedy, we will check it. We will check E, and the current node will be E. And is there any update from E to Z? There will be an update because Z's value was infinite, and 12, the shortest distance to E is 12. That has been proven before. Therefore, 12 plus 5 will be 17. That is the actual cost. Heuristic distance will be is 0. We know that. And the total distance will be 17. And we will be coming to Z through E and update everything. And when we finish, the last thing will be F, which we should check. But when we check, the cost is 17, and that is 20, which is larger than 17. When we even underestimate the cost, we are still higher than the actual one. Therefore, there is no need to explore F. So we are not exploring F, and we are finishing. Now, from A to Z, the total cost will be 17. And that will be from Z to E. Let's go to E. E to D. Let's go to D. D to C. We are tracing reversely. And how about C? C is coming from A. So the actual path is A to C to D to E and then Z. So we should follow that path, and the total cost will be 17. That is A-star algorithm. Now, I think you got the idea. Now it is time to solve another problem with A-star algorithm, which is more complicated than this one. Rather than using table, we will be writing down everything while solving the problem, okay? We will be writing like this. And when I evaluate your papers, I will be looking for those explanations, okay? And you should be explaining how you solved it. Without giving any explanation, you will get no marks. Once again, you will get no marks. Okay, so you have to prove that you know the algorithm. Anyway, these are the cities of Romania. Okay, and what we would like to do, we would like to go from Arad to Bucharest, which is the capital city. What we know the actual distances between each city, but not every city is connected to. It's not a fully connected graph. Some of the cities has got connections to some of the other cities, not all of them. So what we know, I'm talking about the graph now. Those black numbers are the actual costs. Red ones are the estimation from or fly crow, crow fly, kuş uçumu, crow fly, distance from Zerin to Bucharest is 317. For example, from Vaslui to Bucharest, crow fly distance is 199, but the actual distance is 142 plus 85. So I think that distance is not given in here, but the distance between Sibiu and Rymniku Vilsae will be taken as 80 while solving the problem, okay? And also the distance between Arad and Sibiu hasn't been given in here, but in the next slides it will be provided. Anyway, after explaining the graph, what we have the actual distances plus the heuristic values. Now it is time to calculate the shortest distance between Arad and Bucharest without calculating every possible cases. So what we will do, we will start from Arad. If we expand the Arad, we will reach to Zerind, Sibiu, and Timișoara, since Arad has got 3 connections. So what will be the Fn value, the cost? What will be the Fn value for Zerind if the person starting from Arad goes to Bucharest by using Zerind? Okay, by passing through Zerind, what will be the estimated cost, Fn? So the actual cost to reach Zerind is 75. And the estimated cost to go to Bucharest from Zerind is HN 374. Where is that? 374 and 75. That will give us 449. That purple or blue, whatever, I mean, whichever color you are seeing, I don't know. Purple, for I can see that it is purple in my computer. That 449 is the Fn value for Zerind. We have calculated it. You have to supply all these values in your paper. Then we calculate Sibiu. The actual distance is 140. It hasn't been given in here, so the distance is 140, the actual cost. Okay. So 140 plus 253 will give us 393. And reaching to Timișoara will be 118 plus 320, which is 447. Now we are done with Arad and we don't need to calculate anymore. I'm emphasizing this because there are some mistakes in the following slides. Therefore, please don't forget that once we are done with the node, we are not going back. Therefore, we calculate the 3 possible places, Zerind, Sibiu, and Timișoara, and calculate the costs, which is 449, 393, and 447. Now, which node will be the current node after evaluating this? Since the algorithm is greedy, the smallest one will be chosen. Therefore, we will go to Sibiu. Now it is time to expand Sibiu. Therefore, we will be expanding Sibiu by checking Fagaras and Rymniku Vilsae. Therefore, after calculating and saying that from these nodes, Sibiu has the least Fn value, therefore Sibiu will be selected. You have to write it down in your exam paper. Then we have to expand Sibiu. When we expand Sibiu, we are here, and don't forget that we already explored Arad, so there is no need to going back to Arad because it is ridiculous. Start from Arad, go to Sibiu, and then come back to Arad again, and then try to go to Bucharest. So that is ridiculous. That is not the case. That is not possible. Therefore, this slide is not showing the correct calculation. There is a mistake. So this shouldn't be calculated because we already know the cost. Therefore, going to Sibiu and coming back Arad than going to Bucharest will not be cheaper than going to Bucharest directly from Arad. Okay. Therefore, we should be excluding the already visited nodes from our calculations. Now, if we are in Sibiu, we should be calculating Oradea, Rymniku Vilsae, and Fagaras. Because Sibiu has got 4 connections, but one of them has already been explored, and the unexplored ones are three branches. Now, after calculating, you should calculate the Fn values. Reaching to Fagaras, Gn value for Fagaras from Arad passing by Sibiu and Fagaras will be 140 plus 99. That is the cost Gn. Then the estimated value is 176, and we will find out that 176 plus the current distance, that is 415. Now it is here, and this similarly we will calculate for Rymnik Vilsae. Don't forget that the actual cost is 18, even though it hasn't been shown here. So the cost will be 220. It is here. 100 and the heuristic value is 193, and the total cost will be 413. How about Oradea? For Oradea, 140 plus 151, that will give us 291, plus the heuristic value 380, that will result with 671. Now, I've got 671. Sibiu has already been calculated. 415, 414, 13, and 447. Which city, which node has to be expanded? Since the algorithm is greedy, the smallest one, which is the Rymniki Vilsae, that should be expanded. The next one will be Rymniku Vilsae. Okay. I don't want to go through once again, and don't forget that we already processed Arad, Sibiu, and Rymniku Vilsae. So in our calculations, we don't need to calculate them anymore. Therefore, calculating now we are expanding Rymniku Vilsae. We should be checking Craiova, Pitești, but not the Sibiu, because Sibiu has already been visited. So in that slide, that doesn't need to be calculated, okay? And after using the current distances and the heuristic values, reaching Bucharest through the Pitești will be 417 from here, and 526 from Craiova. It has been calculated here. Now we have got 1, 2, 3, 4, and 5 open nodes. Among them, which one is the smallest? 415. Therefore, we will expand Fagaras. When we expand Fagaras, we will reach to Bucharest. There is no need to calculate Sibiu, because Sibiu is in the list of already visited cities. Okay, so Fagaras has been visited. And when we check, the actual cost is 450, and the heuristic value is 0. Therefore, by following Arad, Sibiu, Fagaras, Bucharest path, the cost will be 450. Since we reached Bucharest, the algorithm stop? No, because the termination condition was check whether any open nodes has lower cost value than the cost value you obtain for the finalization. Now, since we reached Bucharest and checking whether this is the end, the cost is 450. The cost of Oreda is 617, so we don't need to check this one out. Zerint is 449. As you can see, we have got a better option. Maybe is going from Zerint to Bucharest could be less than this path, so it needs to be explored. How about 447? That should be explored as well because it is smaller. How about Craiova? 500, we don't need to explore this one because we will never find out any shorter distance than 450 through Craiova. How about Pitești? 417. Among all of these, 417 is the shortest one. Therefore, we decide to expand Pitești. When we expand Pitești, we don't need to go to Râmnicu because it has been already visited. So that shouldn't need to be calculated. From Pitești to Craiova, there may be an update. So we calculate if the function value is better than the value we give, find, we will update. But we have found 615. The old value was 526, so it wouldn't need to be updated. And how about the other node that we should visit? It is directly to Bucharest. And when we calculate, what we have found, 418. So reaching Bucharest, starting from Arad and going to Bucharest through the Pitești, the cost is 418. Okay, so let me cancel out because these are already calculated. Fakaras has been calculated. What we have now, we have got 450, sorry, we have to update that value with 418 because we have found a better solution. So 418 will be updated. And we have already used Pitești as well. Now the open list, the values are 617, which is larger than 418, so we don't need to consider. 449, which is worse than 418, so we will not consider this one. 447 is not smaller than 418. 526 is not good than 418. Therefore, none of the remaining open nodes can provide better solution than this solution. Therefore, we can stop without further exploring. Therefore, after evaluating these, we find out that the shortest distance between Arad and Bucharest is 418, and that has been achieved by following Pitești, Râmnicu, Sibiu, and Arad. If you check, that is the shortest path, and the cost is 415. That's it. Bu kadar arkadaşlar. Sorusu olan var mı? Bugün, pardon, az sonra şeye geçeceğim, diğer slayta geçeceğim. A-star algoritmasını iki ayrı problemde çözdük. İki farklı şekilde hani çözümü gösterdik. Anlaşılmayan bir şey var mı?
Hocam ben bir şey sormak istiyorum.
Evet, buyurun.
Şimdi hocam bu tekste yazmışız ya, bunların sırası önemli mi yazdığımız? Mesela ben önce 75'lik olan, mesela ilk başladık Zerint'e gidecek olan 75'li mesafeyi hesaplamak istiyorum. Çünkü başlangıçta daha kısa. Öyle mi yazmaya başlayacağız yukarıdaki tekste sıraya? Yoksa hangisini hesapladığımız başlangıçta önemli değil mi?
Yani şöyle, sınav kağıdı için mi konuşuyorsun?
Siz dediniz ya böyle yazacaksınız tek tek algoritmayı anladığınızı anlayayım diye.
Evet.
Evet,
Yani
evet.
şöyle, herhangi bir karşılaştırma yapmanıza gerek yok. Hani ben sonuçta arada açarken kimleri hesaplamış diye bakacağım. Sibiu, Zer'in, Timoşara. Benim için önemli olan bu. Değerleri hesapları yapmış mı? Yapmış. 393, 449, 329 güzel. Bunların her birisi birer puan birer puan alacaksan atıyorum 3 puan alacaksın. Ya da her birisi 0,5 puan 0,5 puan. Sonuçta soru kaç puanlıksa, tamam mı? Arkasından
Hı
benim için önemli olan şu. Buradayken kimi seçtiğini yazacaksın ya. We will expand
hı.
CBU. Önemli olan bunu da yazman. Sonra CBU'dan sonra önce Fagaras'ı mı hesapladın, Rimliku Vilsa'yı mı hesapladın ya da Oreda'yı mı hesapladın önemi yok. Şey anlamında sırasıyla. Ama sonuçta CBU'dan sonra bu üç nodu yani Oredea, Fagaras ve Rimliku Vilsa'yı hesaplamalısın. Sırası önemli
Anladım
değil çünkü
hocam.
görebilirim. Tamam. Yani çünkü kağıtta
Peki.
rahatlıkla görünüyor. Değerler de rahatlıkla görünüyor. Ve bunların içerisinden ben Rimliku Vilsa'yı seçtim diye muhakkak belirteceksin. Buraya kadar her şey
Anladım
yolunda.
hocam.
Her bir adam, her bir araba, her bir adıma puanlar muhakkak veriyoruzdur bir şekilde. Ve eğer bir yerde hata yaparsan hani açık listeyi unutmayın. Açık listeniz çünkü daha kapatılmamış Timoşyaralar, Zenitler varken oldu bunlar hatırlarsanız. Bunu unutmayın. Yani seçiminizi yaparken gözden kaçıveriyor. Bir de en önemli kısım neredeyse sorunun yarısı kadar, puanın yarısı kadarı sonlandırma kriterine veririm. Çünkü tekrarlanan şeylere habire puan vermek çok anlamlı değil. Çünkü bir var olan bilgiyi tekrarla kullanıyorsun. Ama sonlandırma kriteri çok önemli olduğu için. Yani Bükreş'e ulaşmış olmak yetmiyor. Eğer açık nodlarımdan kostu Bükreş'e şu anki ulaştığım kosttan daha ucuzu varsa aramaya devam etmek istiyorum. Yani son slayttaki Piteşti'yi expand etmezsen muhtemelen sorunun yarı puanını alamazsın. Muhtemelen. Çünkü bu algoritmanın çok kritik bir adımı. Onu değerlendirirken buna göre puan veriyorum. Hani sonlandırma kriteri önemli. Bunu bilmiyorsa bu algoritmayı tam bilmiyor demektir. O yüzden yarısını buraya veriyorum. Anlaştık mı? Hüsnü.
Anladım hocam. Bir de şunu sormak istiyorum. Mesela bulduk en kısa yolu ama daha algoritma devam ediyor. Daha küçük değerlerimiz var. Mesela Zerin'de hesaplamamız gerekiyor diyelim. Timi Sawyer'ı hesaplamamız gerekiyor. Onları da yazacak mıyız? Onları da göster. Ya bulduk en kısa yolu ama hani onlar da hesaplamaya devam etmemiz gerekiyor
Hayır,
algoritma
hayır, hayır,
gereği.
hayır, hayır, hayır. Gerekmiyor işte. A star aramıyor. Bulduktan sonra cost'lar yani estimated cost'lar actual cost'tan daha büyük kaldığı anda algoritma sonlanıyor. Artık
Hı.
devamını
Orayı
hesaplamana gerek yok.
anladım orayı hocam ama eğer değilse hesaplamaya devam etmesi gerekiyor değil mi? Az önce
Muhakkak.
yaptığımız gibi.
Evet,
Çünkü fakat
muhakkak.
ya onları da mesela biz bulduk. Diğerlerini de hesaplamamız gerekiyor algoritmayı. Onları da göstermemiz lazım.
Evet, tabii
Sonra
ki.
eğer küçükse ya bizim yolumuzdan daha iyi bir yol değilse e, bu yol bulduğumuz yol diyeceğiz. Ben tam
Tabii ki.
anlatamadım herhalde de.
Yo, yo, ben senin söylediğini anladım. Dedin ki sen bana. Senin söylediğin şey şuydu. Piteşti yolundan gitmeden önce Bukreş'te ulaştık ya burada. Ve acaba daha iyisi var mı diye baktığımda daha sonraki denediklerimin hiçbirisi 450'den daha iyi olmayabilirdi dedin. Doğru mu?
Evet.
Bu durumda ne olacak? Tabii ki Fakaras üzerindeki yol olacak. Ama sen diğerlerini öyle bir noktaya gelecek ki bu araman artık da daha fazla aramana ihtiyaç kalmayacak zaten.
Anladım.
Yani şuralardaki bulacağın değerler öyle abuk hale. Mesela Zerind'i baktığın zaman Zerind'den nereye? Oreda'ya gideceksin. Oreda'ya gittiğin zaman üzerine bir 71 daha koyunca daha fazla gitmenin bir alemi kalmayacak. Zaten
Hı hı hı.
Oreda'dan
Hı.
gitmenin bir anlamı yoktu. Öyle değil mi? Hani
Evet.
varsayalım ki Piteş'ten bulamıyor. Kroyova giderek uzaklaşacak. Onun da bir anlamı olmayacak. Timoşuar da habire değeri artıracak. Zaten bir adım sonra bitecekti. Eğer
Hı hı
Piteş'ti
hı.
bu
Hı.
kreş arası daha kısa olmasa yani 101 kilometre olmasaydı da atıyorum 201 kilometre olsaydı o zaman zaten bir adım sonrasında da bütün değerler 450'den daha büyük çıkacağı için algoritma sonlanacaktı. Tamam. Yani
Hocam
sorduğun
anladım.
soruyu
Teşekkür ederim.
doğru anladım.
Şu timi sonra peki Fn'i 447 yerine 400 olsaydı şeyden daha düşük olacaktı hesapladığımız testi yolundan ve
Bir
hesaplamaya
testi
devam
yolunda
edecektik oradan.
413'lü devam edecek tabii ki. Çünkü daha iyi bir seçeneğin olma ihtimali var.
Anladım
Tamam?
hocam. Teşekkür ederim. Tam olarak
Tamam. Tamam.
kavradım.
Önemli olan da bu zaten. Hani sonlandırma kriterimiz zaten bu. Yani Bükreş'e ulaştığımız değerden daha düşük bir Fn değerine sahip açık node varsa, open node varsa algoritma dönmeye devam edecek. Ta ki bütün open nodlar, açık nodların Fn cost değerleri Bükreş'e ulaştığımız o değerden daha büyük olana kadar.
Anladım hocam. Teşekkür ederim.
Rica ederim. Başka sorusu olan var mı arkadaşlar?
Yok hocam,
Sınavda tamam.
göndermem.
Geçen sene ya da bir önceki sene yine bu haritayı vermiştik. Soruyu şöyle sormuştuk. Timoşuar'dan ya da Lugoj'dan atıyorum nereye gidelim? Bükreş'e gitmek. Yani Lugoj'dan Bükreş'e ya da Lugoj'dan Vaslui ya da Urgečania'ya gitmenin en kısa yolunu sormuştuk. Yani derste Arad'la Bükreş'i verdik. Sınavda başka iki şehir arasındakini istedik. Dolayısıyla hani zaten her şeyle aynı ama sizin bulmanız gereken şey hani algoritmayı biliyorsunuz nasıl olsa teker teker hesaplamanız istenmişti. Fakat şöyle bir şey oldu. Arkadaşlarımın tamamı Arad'la çözdüğü için başlama yerimiz yanlış hatırlamıyorsam Zerint'ti. Zerint'ten başlamak yerine hepsi Arad'dan başlayarak çözmüşlerdi. Yani çok büyük bir kısım. Hani atıyorum 200 kişi alıyorsa 50 kişi bu şekilde çözmüştü ve yazık oldu çözdüklerine. Yani çünkü soruya doğru yerden başlamadığı için tüm ara basamakları yani biraz şöyle hissettiriyor insana. Ezberlemiş hissettiriyor. Yani soruyu okumamış çünkü. Ve ya yardımcı olacak kağıtta bunlar yazıyordu. Kopya çekiyordu demek istemiyorum ama yani muhtemelen öyle. Çünkü elinin hazırında var böylesi bir şey. Soruyu yanlış okuma lüksümüz yok arkadaşlar. Çünkü soru ne istiyorsa sizden onun cevabını istiyoruz. Bir de şöyle bir şey var. Siz kalkıp farklı bir şey çözdüğünüz zaman sınıfın geri kalanından sadece birinci öğretimlerde 130, ikinci öğretimlerde 135 mi öyle bir şey. Yani toplamda 270 kişi veyahut da daha fazla öğrencinin kağıdını okuyorum. Ve belirlenen süre içerisinde kalkıp herkesin özel çözümüne yeniden bir değerlendirme puanı, bir anahtar hazırlamam mümkün olmayacağına göre soruya doğru cevap verme, soruyu doğru anlayıp ne istendiğine doğru karar verip çözmeden siz sorumlusunuz. Ya ama hocam ben burada bildiğimi ispatladım dediğiniz zaman inanın kağıtlarınızı okurken ne isminize bakıyorum ne cisminize bakıyorum. Sadece o kısma bakıp oraya göre değerlendiriyorum ve anahtarıma göre değerlendiriyorum. Hani hayal kırıklığı yaşıyoruz ya sınavlarda. Gerekçesi de zaten bu. Keşke sınıf sayımız küçük olsaydı ya da sınıfımız böyle olsaydı da birden fazla hoca veriyor olsaydı da üzerimizdeki yük bu kadar ağır olmasaydı. A-star algoritmasıyla ilgili şurada konuşmadığımız yerler var ya arkadaşlar. İşte burada da zaten işte açık olan nodlar, hani açık olan nodların listesi üzerinden bakılır, en küçüğü alınır falan filan diye uzun uzun burada anlatıyor zaten. O yüzden hani o tarafı okumadım. Anlatırken hepsini söylemiş oldum. Bir de ders anlatırken ben daha çok algoritmayı anlatmaya sizin kavramanız için çaba sarf ediyorum. Textbook bilgilerini çok fazla önemsemiyorum işin doğrusu. Herhangi bir yere Google'a yazdığınız zaman bunun pseudo kodunu da bulursunuz, hazır yazılmış kodunu da bulursunuz, etc. O yüzden algoritmayı anlamış olmanız önemli. Algoritmayı anlamışsanız ileride kendi algoritmanızı özel durumlara has yeni algoritmalar geliştirebilme şansınız olabilir. Mesela atıyorum bir problem vardır. O problemi çözerken siz rahatlıkla daha önce literatürde olmayan yeni bir algoritma yaratabilirsiniz. Çünkü neyi niçin yaptığınızı biliyorsunuz Bir sorunla karşılaştığınızda onu aşabilmek için mevcut algoritmaları nasıl değiştirdiğimizi görüyorsunuz. Dijkstra'ya, çünkü normal bildiğimiz Dijkstra'dan bir fark yok. Hangisi daha greedy bir şekilde yaklaşıyor? Astra için konuşuyorum. Aynı şekilde her zaman en küçüğü expand ederek gidiyor vesaire. Fark nerede? Şeyde bir heuristik eklemiş. Yani bir direction. Hani directed search yaptırmış. O heuristic value sayesinde. Gibi. Burayı bitirdik. Eğer Astar'la ilgili bir şeyimiz yoksa bir sonraki slaytlarımıza geçeceğim. Yok galiba. Hadi geçelim. Ne demiştik? Optimization algorithms. Evet. Slide'lar. Aklıma bir şey geldi de acaba göstersem mi diye şey yaptım. Şurada nerede? Burada yok galiba. Sorular göre sınav soruları. Şu klasör var ya arkadaşlar. Sizin için harika bir yer. Yapay zekada şimdiye kadarki sorulmuş tüm sınavlar burada var. Bir ele geçirseniz burayı müthiş olur. Neyse. O geldi aklıma da şimdi. Sakın öyle bir şey yapmaya kalkmayın. Tüm sorular orada var yani. Bütün girdiğim derslerin, görüntü işlemi, mikronun soruları, dijitalin soruları hepsi aynı klasörde. Neyse. Optimization algoritmasını bir anlatalım. Slaytımıza başlayalım. Yarısını anlatacağız bunun. Diğer yarısını haftaya bırakacağız. Şimdi şu ana kadar, up until now, all the algorithms we discussed were deterministic algorithms, except A star. A star had some heuristic information inside, so integrated to the Dijkstra's algorithm. Therefore, if an algorithm is deterministic, the results will be guaranteed to be same all the time. I mean, whenever you solve the problem deterministically, you will get the same result all the time. But if there is any heuristic information inside the algorithm, then that result cannot be guaranteed. Of course, if the heuristic value is an estimated value in a table, as it's provided in A star, then depending on how many times you solve the problem, you will get the exact same solution because everything is fixed. But while solving some complex problems, rather than using deterministic values, we use some randomness. We try, how can I say, we integrate some randomness to the solution in order to find better results. I will be explaining this throughout the semester from now on. But first of all, from now on, we will be dealing with algorithms that is not deterministic, but it has some arbitrary solution. It contains some heuristics, but they are random heuristics, okay? We will be talking about this later on. But first of all, let's talk about optimization algorithms and their properties and what are the challenges. If we have got a problem, first of all, we should be able to create a solution for that problem, and then we should find a clever way to calculate the fitness or goodness of that solution by using a function. That function should be written by yourself or should be provided by an expert to you in order to evaluate a solution. one of the, I mean, I have given an plain wing problem for Turkish class. Now I will be giving another example. Let's say a TSP problem. We have got a TSP problem, traveling salesperson problem. Of course, this is discrete. It is not continuous like this. Okay, in here, all the graphs are for continuous function. But in here, TSP problem is discrete. Anyway, as you know, with TSP problems, there are in this example, there are 5 cities, and there is a person who wants to visit every city once and only once. That is the most important aspect. Every city should be visited once and only once, and the person should return to the city that it has started to its journey. The traveling salesperson should return back to the city that it started at the beginning. So the names of the cities, let's say A, B, C, D, and E. And if I say write a solution, I want to change the color. Let me put it as green. Now for the 5 cities, I'm writing a solution. Go to, let's start from A, go to D, then go to B, then go to E, then go to C. Is this a solution for the problem for a traveling salesperson? Yes. Is it a good solution? I don't know. But I created a solution for the person. It can visit every city once, and he can or she can go back from the last city it visits to the first city that it started. And may I evaluate this solution by using a fitness function, a goodness function, by using a function? Yes, of course. If we know the distances between each node, then I can easily calculate the total distance covered by that person who is using that suggested or candidate solution. Imagine that we are provided with a table. We are provided with a table that is showing every possible distance and saying that if the person follows that path, the total distance he covers is 1,400 kilometers, for example. How did I write this solution? Randomly. Is it a good solution? How can I evaluate this? By adding the distances between relevant corresponding nodes, and I can find the total tour length, and that will be my fitness value. So as long as we can write a solution, but the problem, the main idea is that solution doesn't necessarily be to be the best solution. As long as we can suggest a solution, we are fine with it. Okay. So did you understand what I mean by saying that suggesting a solution? Just propose a solution randomly. It can be any solution. As long as it solves the problem, that's good. Then evaluate whether this solution is a good one or not. And in order to say that is a good one or not a good one, we need to compare it with another solution. So what we will do from now on, we will have a solution and we will compare that solution with another solution, maybe written randomly or by using some intelligence, and by comparing them and selecting maybe greedily the better solution and moving forward, we will be aiming to reach the global solution, global best solution. Okay? Do you have any question about this writing solution for TSP problem and evaluating it? As I told you, that is discrete one. Imagine, for the simplicity, imagine that we have got a problem which is, hold on. Now, imagine that we have a problem, and that problem is the function of PR. PR is the pressure value. So what we want to do, we want to minimize to obtain minimum fitness value that is given by, that fitness value is dependent on a single variable which is called pressure. So imagine that FPR sorry for that, FPR is given here. Therefore, that axis has to be PR. And when we evaluate every possible cases in a continuous domain of pressure, what we came out with the fitness value, something like this. And what we are looking for, what we are searching for, we are searching for the value, pressure value that minimizes F function, FPR function. If we know the mathematical expression of FPR by taking the derivative and making it equal to 0 and solve it, you will find out where the local minima and maxima is, okay? Minima and maxima, in these points, the derivative of the fn function will be 0, okay? As well as, of course, there are some local minimas and maximas, but if we know the function, at least we can estimate those PR values, and among them we can select whichever is the minimum, okay? By this way, deterministically we can calculate where the global minima is, okay? This problem is, pardon, yine deprem oldu gibi bir ses geldi arkadaşlar. Değilmiş, pardon. This problem has only one parameter, dependent parameter, and it is easy to draw such function if you know the function. But in some cases, the problem may have more than one parameter, one dependent parameter, okay? So if the problem has got, let's say, 20 parameters that is affecting the solution, it will be impossible for us to draw fn function because it is in 20 dimension, and we cannot draw functions more than three parameters, 3 dimensions. Therefore, by looking at where the local minima or global minima will not be possible because we are not able to draw it, and also depending on the search space, there may be many values that has to be evaluated. Anyway, so let me talk about local maxima. What is local maxima, local minima, global maxima, and global minima means? As I told you that if the problem is minimization, what we are actually looking for, we are looking for the solution that has the minimum value. That is called global minima. There are some values which is minimum within the vicinity of, or within the within a certain part of the search space. So that is the solution which has the minimum value where within this neighborhood, and this is a local minima. There may be, actually there is, but there may be some minimum values even less than what we have found here. If we expand the search space up until here, and we will come across that there is another minimum point which is better than this one. So therefore this will be a local minima, but that one will be global minima. So if the problem is a maximization, we are looking for the maximum points, and there are some local maximas and global maximas, okay? So usually in an optimization problem, we are looking for the best solution. That best solution is either maximizing the point we are trying to get or minimizing the point we are trying to get. When I say point, actually, I'm talking about the fitness value, okay? We want to obtain the lowest distance for TSP problem, okay? Maybe maximum profit for an sales problem. Anyway, so now what we know, PR is a dependent variable. Fn is the fitness function depending on PR, and we should be able to write a fitness function to evaluate the goodness of a solution. Okay, and now P and FP is given, and what we are looking this is that, and if you know the function, we can easily draw that one, and if we that graph, and if we are looking for that global minima, we will try to find out which value is giving that one. So actually this problem is we are trying to find out which P value minimizes this function. Okay, and as I told you, take the derivative and make it equal to 0 and find out among them whichever is the minimum, you can get the result. The whole space in here is called problem domain. Even though it has been shown in 2 dimensions, actually, since there is one parameter affecting the problem, our problem domain is 1 dimensional. Actually, it should be traced in here, but rather than showing in 1 dimension, I have given you in 2 dimensions, but don't forget that actually we are talking about 1-dimensional problem, because since the problem has 1 dependent variable. If it was 2-dimensional, then we need to use the 3rd dimension to print out the fitness value, and that will be difficult to display. Actually, I will be showing you in the next coming up slides 2-dimensional problem with the fitness value. Anyway, if we would like to find out the global minimum, we should have some prior knowledge. Okay, I've told that to your friends. Imagine that we are trying to design a plane wing. Okay, and while designing the plane wing, there may be hundreds of parameters to be considered, but let's talk about the length, or not the length, but the width of the plane in one cross section. What will be the length of a plane, the width of the plane for a normal or an abnormal plane. The length could be, let's say, minimum 2 meters, maybe 0.2 meters, maybe up until 50 meters. That is quite absurd, but rather than searching the whole space, what we will do, we will be limiting our search space with the lower boundary and the upper boundary. Lower boundary is 0.2 meter for a wing, and the upper boundary is 50 meter. How did I get these values? I just intuitively decided on those values, which means randomly. But if an expert, aviation expert, tells us that design your plane with the minimum wing length is actually 2 meters and 5 meters, that is quite narrow space, and within I mean, this lower and upper boundary, maybe the design will be what they are looking for. Therefore, we need some information in order to find the best solution, and that's information should be coming from an expert on the field. And by doing so, we will be limiting the search space, and chance of finding the best solution will be increasing. Rather than dealing with the whole problem domain, what we will do, we will be narrowing down the search space. By this way, we may reach the best solution in a shorter time. The wider the search space, the longer time it will take to calculate. Okay, so if we know the lower boundary and upper boundary, how can you suggest a random solution for P, for the problem? So what I mean is, how can you write a random point if you know the lower and upper boundary? Okay.
Problem, pardon.
Söyle lütfen.
Problem domain'den rastgele bir alan belirleyip
İşte
o
upper ve
alanı
lower
seçiliyor.
boundary, hayır, lower ve upper boundary arasında rastgele bir değer üret. Yani sana şunu soruyorum. What I'm asking you is, between 2 and 5, I have given you as an expert, I said lower boundary is 2 and upper boundary is 5. Suggest me a solution for the problem between 2 and 5. Just give me an example. What can be a solution for P?
3 olabilir.
It could be 3, right? So how did you decide on 3?
Ya ikisi arasında rastgele bir
So what
değer
you have
belirledim.
done, you have randomly chosen a value, okay? If it was between 0 and 5, it was easy, because if you throw a random number between 0 and 1, imagine that a random generator is producing numbers, floating point numbers between 0 and 1, minimum 0 and maximum 1, okay? So within that range, it is producing numbers. If I multiply this with 5, which is upper boundary, what will I get? I will get the values. If random is 0, it will be 0. If random is 1, it will be 1 times the upper boundary, which is upper boundary, which is 5. So if I use random times upper boundary, it will produce me the values between 0 and 5, right? But what I want between 2 and 5. So how will I do this? I will take the range. The range is upper boundary minus the lower boundary, right? Which is 3. And if I randomly multiply this, what will I get? I will get any number between 0 and 3, because upper boundary is 5, lower boundary is 2, 5 minus 2 is 3. When I multiply it with random, which is either, which has values between 0 and 1, at the minimum it could be 0, so the 3 times the 0 will be 0, and at most it can be 1, so 3 times 1 will be 3. So I will be producing numbers between 0 and 3, but what I want between 2 and 5, and if I add lower boundary to this, what I will get, 2 plus 0 means 2, 2 plus 3 means 5, so I will get values between 2 and 5. So that formula will produce me a number between upper boundary and lower boundary. Okay, I just finalized it. So upper boundary of P minus lower boundary of P, multiply it with random and add it to the lower boundary of P. Let's say 8 and let's say 10. Okay, so 10 minus 8 will be 2 times the random plus PLB, which is 8. Okay, so give me a random number between 0 and 1.
Maybe 9.
No, 0 and 1, between 0 and 1.
0 and 1.
0 and 1 is inclusive, but any number, any floating point number between 0 and 1.
Then.
For example, 0.9, your friend said. 0.9 times 2 is 1.8. Plus 8 will be 9.8. So what will I do? Where is that? Okay. Kalem, hold on. Something is wrong. Kalemi bulamıyorum arkadaşlar burada. So if the value is 0.9, then random solution will be produced in here, and we will be checking whether it is a good one by looking at. So our candidate solution will be here, okay, because the random value was 9. So what I was trying to do, that random number could be at most 1, at least 0, and the values could be between these two. So by looking at the extremes, I can easily calculate where the other values will be calculated. Therefore, if it is 0, 2 times 0, because the range is 2, 2 times 0 plus 8 will give me 8. So if random numbers is 0, I will get the lower boundary solution. Any number between in here will be giving me solutions somewhere here. At most, random number will be 1. 1 times 2, 1 times the range will be 2. 2 plus lower boundary, which is 8, is 10. So at most, I will get this solution. So depending on the value of random number between 0 and 1, I will be landing up any solution within this range. Okay? So this formula is used for, this formula is used to create a random solution within the lower boundary and upper boundary, and yes, upper boundary and lower boundary with randomness, and that random function is producing numbers between 0 and 1 inclusive. Do you have any solution? Do you have any question? If the problem was two-dimensional, I could ask this one. What will happen? I will be applying this function to each dimension. So I will be saying that randomly I produce that solution for P dimension. Let's say the other one is called k, and randomly I will be producing a k value. So the coordinates will be p and k. So that will be our solution, and we will come up and say that this, of course, the function will be two-dimensional. In this case, function will be depending on k and p, k dimensions and p dimension, and then we will check the result and how good it is. We will be calculating the fitness of that value. Okay, so if the problem is more than one dimension, for each dimension you have to produce a random solution. Okay, do you understand what I mean? If the problem has got 30 dimensions, you have to do this for every dimension, and every dimension will have lower boundaries and upper boundaries, and according to that we will be creating a random solution. Now, since we obtained a solution, now what we want to do, we can randomly select another solution and check which one is better, and we can, a naive approach to find the minimum point or the optimum point, just create random solutions and let's say hundreds of them. Whichever is the smallest, you may say that that is my solution. Is it the exact global value, exact global minimum point? No, but at least among randomly proposed solutions, among the 100 randomly proposed solutions, the smallest FN value will be giving you the best solution within that set. But actually, that doesn't necessarily to be the global minimum point. But another thing we can do is maybe improve the solution we have found. So we have one solution. Maybe within the neighborhood of this solution, we can produce another solution, which we will use frequently in the upcoming algorithms. So by adding d, distance, neighborhood radius, or subtracting d plus minus d, we can find a solution within the vicinity or the neighborhood of candidate solution. Okay, so maybe I will be producing another solution in the neighborhood of this one, and I will check the goodness of it, and when I compare it, that new solution will be better. So I will be moving to that point, then I will check, or I will be producing a new solution within the neighborhood of that solution, and if I find out a solution in that direction, it will be better. But if it is on the other side, it will be worse. If the solution is worse, I will not accept. But if it is better, I will accept it. And when I follow that rule, I will end up with coming up to local minima. But at least I will find the local minima rather than randomly producing values. Produce a value, produce a solution, and improve it, or find another solution within the neighborhood of that solution. Whichever is the best, keep that one and produce another solution from the better solution. And if the solution has a better choice, it is better, accept it, otherwise reject it. And by applying these several iterations, you may end up finding a minimum point. Did you understand what I mean? A simple idea. In order to do this, you should be able to produce produce solutions within the neighborhood of current solution. Therefore, if the neighborhood radius is d, so we are looking for plus minus d distance, the formula will be like this, which means pi is our current solution, d is the distance between in the plus direction and minus direction from the current solution, and pi minus d plus 2 times the radius times random number will give me a new solution within the neighborhood of current solution. Let's check. Random could be in the extremities, could be 0, 1, or any number. And let's say the neighborhood is 5, for example, or let's say the neighborhood is 1, or tell me, just give me, let's say D is 3, okay? So from the current solution for P, let's say the value of P is 2.5. So what we are expecting to find a solution somewhere between, tell me, minus 0.5, right? And 5.5. Why is that? Because we are currently at 2.5, right? 2.5. So plus minus plus 3 will give me, if it is minus 3, it will be minus 0.5. If it is plus 3, it will come up to 5.5. So the solution should be somewhere between these two values. And let me check. Since pi is 2.5, d is 3, 2 times 3 is 6, times the random. What is the random value? Let's say at the extremities it is 0, so that will go to 0, and it will be 2.5 minus 3, it will give us minus 5, okay? Minus 0.5, sorry. So any number between this one and at the extreme, it will be 1. If it is 1, that value will be 6, because 2 times 3 times 1 will be 6. 6 minus 3 will be positive 3. So 2.5 plus positive 3 will give us 5.5. So therefore, depending on the random value, we will be producing a new solution somewhere between minus 0.5 and plus 5.5. So it could be any number if we use that formula. I think it is clear. Is that clear?
Yeah, it's
Okay.
clear for me.
Okay. Therefore, by producing new solutions within the neighborhood of the current solution, and we will evaluate it, the naive approach, if the new solution is better, then accept it. Otherwise, reject it and produce another solution. And we will be hoping that we will go down and find the minimum point. But this minimum point could be a local one, and there may be a global solution, global best, within the upper and lower boundary. So I said the approach is naive. Naive means saf, yani basit, çok kompleks olmayan dümdüz bir algoritma. So now we have suggested a new algorithm, let's say. That algorithm is working like this. Create a random solution, and within the neighborhood of that solution, create another solution. If the new solution is better than the old one, accept it, and that will be your current solution. And within the neighborhood of that solution, repeat the process once again, which means create a random solution within the neighborhood of it. And if it is better then accept it. Otherwise, reject it and create a new solution where within the neighborhood of that solution. And by this way, you are hoping that you will be declining from the point you are where you are, and you will be going down to find out minimum point. Okay, and it has been illustrated here. Should I accept it or decline? If the problem is a maximization problem, I will be accepting it. Otherwise, I will be rejecting it. In here, I have shown you, if what we have done, we just suggested a new algorithm, okay, which is a naive. Actually, this algorithm has already been around for at the beginning of the computer science, computer engineering, because it is too naive that it is the first algorithm that come up to mind. Anyway, what we should do, if we have got some idea about solving problems, a new idea maybe, what we should do, we should try it on the test functions. These test functions are proven to be difficult, proposing the challenges to the algorithms we are proposing. Therefore, if they pass, if they can find the minimum or maximum points of these functions, then we say that that algorithm can be used to solve common problems, and it's a good algorithm. So what we will do, I will introduce you a hill climbing algorithm, which is capable of solving many problems, and simulated annealing genetic algorithm, anti-colony optimization algorithm, etc. So they are all proven to be able to solve complex problems such as this. What I mean is, as you can see, that problem domain has got two parameters. Okay, it is two-dimensional, and the parameters are x1 and x2. Okay, and fitness value has been drawn in color, so that's why it is in 3 dimensions. So this is a two-dimensional problem, but you have to draw it three-dimensional because f function, the f values should be shown in here. And if the problem is a minimization problem, what we should know, we should find x2 value should be that value, and x1 value should be that value, for example, and saying that that is the best solution. If we find the best solution, that's the minimum point, then we will say that our algorithm finds the minimum point for camel function. So check, it's a good one. How about judge function? You will randomly create a solution, and by accepting or rejecting it, you will be following the downward and you will find the minimum. But if the minimum solution is here and you create a random solution somewhere here, so the algorithm will be going down and it will never come up because it will be trapped under local minima. But at the beginning, if you produce a solution somewhere here, then it will be going downward and it will find the global. Maybe you will find it here and it will be going under each, maybe it will go down here, so that will cause a problem. So there are many challenging stuff for an algorithm to be proven that it is working for generally. Another algorithm you have to pass with Langerman test function. Imagine that you want to find out the minimum point, and if you produce a value, if you produce a solution, and if you try to improve, when you come up here, you have to go worse because there is, in order to go down, you have to climb first. So in order to reach that minimum point, first of all, you have to climb up to the worst solutions. Then once you are in, you should be able to find the optimum solution. So the naive approaches will be failing, but more complex algorithms will be finding the solutions. Another one, test two-polar functions, etc. Now, as you can see, because we test our algorithms by using the known functions, but in real life we don't know the mathematical equivalence of the function. Therefore, we cannot guarantee that this algorithm is working. So what we do, we use test functions and prove that it is working on that test functions. Then it will be widely acceptable by the people to solve some certain problems by using your proposed algorithm. Now, what I told your friends, that imagine that we are somewhere here, and when we, within the vicinity, if we produce another solution, that solution will not be different than the previous one. Maybe it will have exactly the same value. If you think that this area is completely flat, that is flat, but there is a hole in it, like a needle, and the minimum point is here. So even though the algorithm is not improving when you produce solutions, you may never come up with the best solution if you only accept the good ones. So time to time, you should be accepting moving around even though the solutions are not good. So we should be integrating some new strategies to our search algorithm to be able to find the solutions in a complex systems. For example, I told your friends that imagine that we have got a fly. Okay, as you know, flies, how can they fly? You know, I'm talking about insect fly. They just come up and buzz, it will be, you know, when it will be making small movements, then radically go somewhere else, and it will be making some small moves, then randomly goes another place and searches, and then searches like this. Okay, that is the typical behavior of a fly while flying. And look at the karasinek, or look at some other small flies. They will be following, you know, completely random sudden moves, but whenever they land, they make some small movements like this. Actually, this is what they are doing. Actually, they are searching, they are exploring the surface area. So they are exploring the space, and when they reach somewhere, they exploit that area by making small moves, then later on radical movement, and then they go somewhere else and search on that area, etc. So the algorithm, the search algorithm a fly does is makes two important movements. The first one is exploration, the other one is exploitation. These terms are important because if you have a search algorithm, that search algorithm should satisfy the exploration property and exploitation property in order to be successful to find out the global optimum point. Exploration is the process of finding a new region, searching for the best solution. So those sudden movements are finding new region of the search space. You are just leaving where you are, radically going away. That is exploration. But if we are in a place and just trying to find out a better solution within your neighborhood, and you are checking every single possible cases within your neighborhood, that will be exploitation. In Turkish, we call this didikleme. You are you are exploiting a certain part of search space, and by the hope of finding a better solution. But once you get stuck in a local, then you should make a sudden move to, you know, break through. Let me go to that drawing again. Oh, that's too dirty. Okay, for example, in here, imagine that we are here and we followed down and we got stuck and we are exploiting here. Then randomly making a big move, maybe here, and go and find the minimum point and start exploring. Then make a sudden move and come up here and follow down, and you will find up, and you will end up with the global point. So making sudden moves means exploration. Making small moves will be exploitation. So the naive algorithm has been improved by adding some random radical changes. Rather than producing new solutions within the radius of neighborhood, if I integrate a sudden movement, a large value change in the neighborhood, it may help me to escape from the local minima, and they may help to find me and make me to find a global minimum point. Okay, so the idea was very simple, and I just added a small touch. I just made a small touch, and the algorithm became more efficient. Okay, why? Because I know that exploration and exploitations are two important aspects of a search algorithm. Okay, I just talked about it. And hill climbing is working like this. And I will be talking about hill climbing and simulated annealing next week. Okay, the last thing is a good search algorithm should balance both of them. So there is a balance. Your algorithm shouldn't be mainly exploitating or shouldn't be exploring frequently. There is a balance, and that balance is actually, I'm just telling this, but that's not a certain value, but my experience says that 75% of the time we should be exploiting, 25% of the time we should be exploring. So mostly exploiting and rarely exploring. In the morning, I told my friends that in a society, if we are conservative, what we are doing actually, we are preserving our gains from the past. So making only small changes from our lifestyle because we are conservative, that means we are exploiting our culture within the vicinity, close vicinity of our own culture, our past, our culture passed through us by our ancestors. There are some liberals, some outcasts, which they live, maybe for some people, they are living in outrageously, but actually they are exploring the culture or exploring the search space by the way they do, and they may come up with some new ideas, some new cultural ideas, maybe some other ideas, and the whole society may benefit from them. If a society is completely made up with conservatives, there will be no movement. There will be only a small improvement. If it is completely people with liberal thoughts and they can do whatever they want freely. In this case, it will be chaotic. There will be no. The society will not be in a harmony. But the best thing is mostly conservative, but there are a certain part of people should be exploring things. I mean, of course, you cannot do this forcibly, but the societies are already solved this problem anyway. So in a society there are every kind of people, and believe me, all these people are helping each other to go to better, to make it even better. And it is quite understandable that being conservative is not a bad thing, but it is not such a good thing that, how can I say, it is not brilliant, because if all the people are conservative, then there will be no movement, there will be no advancement. If they are always exploring, then there will be no, the society will not be going in harmony. What I mean by saying that all the values will be fluctuating and everything will be chaotic. Therefore, there should be a balance. A certain amount of people should be doing their role, playing their roles, and another people should be playing their roles, etc. We can talk about this later on. Anyway, that's enough for this week. Next week, I will be talking about hill climbing, then simulated annealing. After that, we will start to genetic algorithms. And so next week will be quite busy. Do you have any question?
Hocam kendi adıma.
Yok. Öyle mi? Var mı?
Yok hocam, gayet anlaşılırdı bence.
Gayet anlaşıldı. Gayet de uzun, saat 7:30 olmuş. Oo, epey olmuş. O zaman bugünlük bu kadar arkadaşlar. Haftaya devam edeceğiz. Ben kapatıyorum kaydı.